All right, people, welcome to section 7.3, sample means. This is so exciting. We're finishing up our exploration of sampling distributions. This is going to set up the rest of the year, right? If you get chapter 7 down, pretty much everything else we do the rest of the year is going to relate to this. And so an understanding of this is going to set you free. So let's go. Sampling distributions from our activities. So we did shoe size sampling, we did age of pennies. Right now, as I'm recording this, we've only done shoe size sampling in one of my two classes. We haven't done age of pennies yet. So I'm going to be kind of guessing at what things are going to look like. Feel free to grab your activity sheets and fill in exactly what you saw with the numbers that you saw here. I'm just going to kind of give a guesstimate for what it might be. Okie dokies. So, shoe size sampling. Let's see. We should have had something. I think it looked, if we drew a picture of it, people said, yeah, it looks pretty unimodal, symmetric. I'm just kind of giving a general thing, but it looks something like this, right? The mean was 9. I think the standard deviation was something around 2 or 2.1 or something like that. Okay. So mean was 9. We wouldn't be surprised to be between 7 and 11. Most of the stuff was between those two. We had some smaller ones and some larger ones, but that kind of gives us an idea of the spread and center of the distribution there. So that was our population. From that population, we took samples. The first time we did samples of size 4. Okay. And when we did that and we found the means, we got something that was squished in a little bit, right? We didn't have anything out here at 4 or out here at 14. We tended to be here from like 6 to like 11 or something like that, right? So our stuff probably looked a little bit more like this, maybe. May not have been perfectly symmetric, right? It is sampling, right? There's going to be variability. But we got something that was definitely more squished in and looked hopefully semi-normal-ish, right? Again, we can't say normal, it's not normal, but we can say fairly normal. All right, the mean of this was probably somewhere around 9, okay? Maybe 9.1, 9.2, 8.7, 8.8, depends on the class, right? And your standard deviation, ooh, I forgot something. Mean of the sample means, right? So mean of the sample means mu of x bar and sigma of x bar. We have to change our thing now because we're not in population land, right? We're in mean of our samples. I took all of your samples that you took and found the average of all of your samples. I took all of your samples and calculated the standard deviation of those samples, right? So the standard deviation of the sample means should have been around 1-ish or so. I forgot the I in ish. There we go. All right. We probably went to something like 10. Again, if this changes for different classes and different years, that's fine. Go ahead and put in what you did because then it's your stuff and it makes a little bit more sense. When we did that, we saw that things got even more like centered, right? Maybe something like this, right? Even more squished in. We were probably between like I don't know, 8s and 10s for the most part, right? Maybe a 7 here and there, maybe an 11 average here or there, but we were getting even more squished in, right? So the mean of our X bars should have been somewhere around 9-ish. Again, could be a little bit off, sampling variability, right? And then sigma of X bar, which was about um, probably like zero point 0.8 or 0.7 or 0.6 or something around there is where it should be about with a sample size of 10, right? If we did a sample size of 16, it might be more, right? Just depends. Cool, cool, cool. All right. After that, we did Age of Pennies. And I'm, again, doing this before we've done Age of Pennies. So I'm just getting at your idea. Again, take your stuff from the Age of Pennies and fill in what you got. I do know um, the first one, if we did a graph of it, should look something kind of, I'm trying to think of what it looked like. I know it's definitely skewed this way, right? So maybe something like this would be the population. Okay. Depends how we graphed it with the histogram, but definitely skewed to the right. Most of the stuff, newer pennies, less older pennies, something like that. The mean of this population distribution is 13, I think. and the sigma or standard deviation of this is about 11. Again, it's pretty skewed, so it's not a great idea to use these two, but we're throwing it out there to show what happens to those two as our sample size increases. All right, the first one was 4, right? And when we did that, or when we do that, because I'm talking about the future here, we're going to see that instead of being severely skewed, we start being a little less skewed, and it starts looking maybe a little bit more closer to normal. Maybe it looks something like this. Again, use yours from what we did in class. Okay, we still probably detect a right skew here, but it's starting to look a little bit more normal. Okay, again, the mean of our X bars should be somewhere around 13. The standard deviation of our X bars, we notice, gets smaller and should be around 5-ish. Okay, like 5.5, somewhere in there. Um, cool. Then we did sampling distribution. I'm going to say we did size 10. Again, different years. Maybe I go to 16 or something fun like that. Um, but if we did that, we kind of notice that now we're getting probably something that looks a little bit more like this. Maybe you're still detecting a little bit of skew to the right, something like that. But we're getting pretty normal here. Okay, it's starting to look pretty normal. So mean of X bars, again, should be around 13. The mean stays the same, right, as the population mean. The standard deviation of our little sample means, again, depending on what we use here, could change. But my guess would be it'd be about 3-ish. Okay, somewhere in there. 3 to 4-ish, but it's definitely decreasing as the sample size increases. Cool. All right. So for both examples, how did the following change as the sample size increase? Well, for shape, let's look at our shoes. Shoes started off being symmetric or kind of normal-ish, right, distribution, and it stayed pretty symmetric and pretty normal-ish. Okay, so if it started with symmetric or normal-ish, it kind of stayed symmetric, normal. Oop, I don't have that on the screen. Stayed symmetric or normalish, right? If it started skewed, though, what happened? If it started with a significant skew, which this was, if it started with a skew, it became more normal as our sample size increased, right? So as we got bigger and bigger sample size, our sampling distribution looked more and more normal. Really important there. All right, the center stayed the same, stayed close to the population parameter, which in this case is mu, right? What happened to the spread? All right, as sample size increased for both of them, as sample size increased, our standard deviation of the X bars went down. So our sampling standard deviation got smaller and smaller and smaller as we got bigger. So less variable, more normal, center stays the center. All right. So let's look at our green sheet, our formula sheet, because it's got all of this that we just figured out here. Okay, dokies. So go green sheet, find sampling distributions and inferential statistics. That's what we're getting into next. This leads to this. Here was the proportion stuff for one proportion and all the good stuff we had here, right? And standard error as well. We have the same thing for means right here, sampling distribution for means. We've got the mean of the sampling distribution equals the mean of the population. Boom. We've got the standard deviation of the sampling distribution equals the population standard deviation divided by the square root of n, right? So this is, well, this is the mean of the sampling distribution. It makes sense, right? So I'll write that here, but you have the words right here. Mean of sampling distribution, that's what that is, equals, this is the population mean. Okay, makes sense? Good. This is the standard deviation of sampling distribution. And that equals the population standard deviation divided by the square root of sample size. We should know that n is sample size. I don't think I need to write that. We also have standard error here. And remember, we talked about standard error before. Standard error is sometimes we don't have the population proportion, so we have to use a sample proportion. Sometimes we don't have the population standard deviation, so we have to use the sample standard deviation as our estimate of it. Okay, so when we use our sample rather than our statistic rather than our parameter, we say the word standard error. It basically means standard deviation, right? It's just standard deviation from the sample, using the sample instead of the parameter. Cool? Statistic instead of parameter. There we go. Cool, cool, cool. Um, let's see. All right, so let's plug them in. So the mean of our sample distribution equals the population mean. We could write that here. Mean of sampling distribution equals the mean of the population. Okay. Again, and this is if we did every single possible sample that was possible, right? Ours, we're going to have variability because we didn't do every single possible sample of size 4 from here. Okay. So theoretically, if we did every single sample that could be of size 4 from here, they would equal. Does that make sense? Okay. Um, we're just kind of getting a demo of it by doing a few of them. All right, standard deviation. Standard deviation of my X bars is equal to the population standard deviation divided by the square root of n. Oops, let's make sure this gets on the screen. There we go. Standard deviation of my sample distribution is, boom, right? And this makes sense, right? As our sample size increases, where is that? There we go, spread. As our sample size increases, the standard deviation of our sampling distribution goes down. We saw that, right? From 11 to 5 to 3, from 2.1 to 1-ish to below 1-ish, right? We saw that it goes down, and this is mathematically how it goes down. It goes down by the square root of n, okay? Kind of like population did in a way, right? Or sorry, proportions did in a way. All right, standard error, same thing, except we are using a statistic, right? So this is sample standard deviation of our X bars is equal to the standard deviation of our sample divided by the square root of n. Okay, so this is from the population. This is from the sample. Okay, these two should be close, right? These two should be close. This is a good estimate, we believe, of this, right? Which is why we can use this if we don't know this. And a lot of times we won't know this, right? We're going to have to use standard error. Oftentimes, again, just like with proportions, they will use SE. You'll see this on computer output quite a bit rather than this, right? SE is standard error. SD would be standard deviation. Cool. All right, that gets us through the front page. That was a lot. All right, now we're going to get to the good stuff here and actually using it, kind of giving you a preview of what's to come. All right, standard deviation versus standard error. The difference is standard deviation, you're using the population standard deviation. For standard error, okay, you're using an estimate from the sample. The sample should be an estimate. Sample is an estimate of the population. If you have both, always use this one. Okay. This one should be better. I hate to say accurate, right? But there's going to be more variability with samples than if you found the standard deviation and asked a census of everybody, right? So it is less variable than a sample would be. Less variation with that. Okay. So don't use the word accurate. It came to my mind because that's the way we describe things in real life. But in statistics, let's not use that word too often. All right, how to decrease standardization of a sampling distribution, right? This deja vu of what we did with proportions, right? To cut it in half, my sample size needs to multiply by, If you said 4, you are correct. To cut it by a third, we're going to take our sample size and multiply by 9, right? Cool, cool. Because it's over the square root of n, right? Yes. Right? So we're dividing by the square root of n. So when we divide by the square root of 4, we're dividing by 2. When we divide by the square root of 9, if they ask you to, they wanted it 4 times cut in quarter or something like that, right? You could do the same thing. All right, check conditions. Just like in proportions, we have to, this is going to lead to some good stuff, right? What we want is a fairly normal distribution, right? When we have a fairly normal distribution, we're able to use normal CDF, we're able to use inverse norm, we're able to use z-scores and all that good stuff, right? So these conditions help get us to that, okay, is the idea. So the three conditions, number one, we need some kind of randomness. Okay, look for it to be stated in the prompt. Look for things like SRS or a random sample of people or something like that. We're looking for the word random or SRS or something like that. It's almost always in there. So just look for it, and that meets that criteria. Good. My nearly normal condition in proportions, it was NP and N1 minus P, but we don't have proportions here, so we don't have that. So we have two options right now. We will add one later on. Population is normally distributed. So if it comes in normally distributed, right, then our sampling distribution should be normally distributed, right? If it's pretty close to normally distributed or it's at least symmetric, then we're pretty good with a smaller sample size. So if they state that it's normally distributed or fairly normally distributed, or if they give you a graph that shows that it's fairly normally distributed, all you've got to do is point to the graph with a little arrow and say, look, this looks pretty fairly normal or fairly symmetric, something like that, right? So that's one way you can satisfy this condition. The other way is if it's not normally distributed, or if you don't know if it's normally distributed or not, okay, is all you have to do is have a sample size greater than 30, right? Look at our, where's my piece of paper? Where'd it go, right? This was a pretty non-normal. This was pretty severe skew in this. And when we got to 10 or 16, whatever you use for yours, we were getting pretty normal by then, right? Imagine if we'd gotten to 30, we'd be in really good shape. Okay. So that's why this one is here. When we have a sample size of 30, that sampling distribution gets pretty darn normal. Okay. This is via the CLT, which we're going to talk about right here. Okie dokie. And then the 10% condition, which we had in proportions. We need to make sure our population is large enough, like how I spelled enough, to support this sample size. Okay, this is for independence, right? So this doesn't really help us with a nearly normal graph, but this helps with independence. And we'll talk about this a little bit more in depth later. But this is the third condition. Make sure our population is big enough to support this sample. Cool. All right, let's move on. Central limit theorem. This is a big one, CLT. All right, if a random sample is drawn from a population with a mean mu and standard deviation sigma, then when n is large, like this one right here, right? When n is large, the distribution of the sample mean x bar, right, is approximate of the sample mean, right, which is x bar, sample mean, is approximately normal. Okay? That's this nearly normal condition is based on the CLT, right? When we have a large enough sample size, right? Even if we have a weird old population distribution, and we'll show you some in class, maybe some really funky ones that once you get up to a sample size of 20 or 30, get really, really normal looking. Okay, that's what it is. And it's important because we want to use normal calculations a lot of the times. They're great to use. They help us approximate probabilities. They're going to help us with a lot of stuff later on. So we'll see a problem right now. So this is from your text. This is question 54 in your text, dead battery. Suppose, I think I changed it a little bit. Suppose a car battery has a lifetime that is fairly normally distributed with a mean of 48 months, about 4 years, and standard deviation of 8 months. It is actually exactly 4 years. Sorry. A company installs a new version of the battery on a simple random sample of 10 cars. If the new version has the same lifetime distribution as the old battery, describe the sampling distribution of the mean lifetime X bar. So to do this, we're describing the sampling distribution. Okay, when we describe, we're doing SOX, right? Shape, outliers we're not worried about, center and spread. So shape, center, spread. What is the shape of this going to be? Is it going to be fairly normal? How do we know? Fairly normally distributed, right? So for shape, I would say it is fairly normal, right? Stated up here. Stated that the population is fairly normally distributed. Cool. There we go. So the shape of the sampling distribution should be also even more normally distributed than fairly normally distributed, right? So center, right? The center should be the same as the current. The current mean is 48. Okay, so the center, the mean of my sampling distribution should equal the mean of the population, which should equal 48. And then my spread, again, I should be showing you this, right? This is right here on our green sheet, right? We can go through it. The mean, the standard deviation, standard error if we need it. Here we have this one, right? So the mean of the sampling distribution is just the population standard deviation over square root of n. So the spread, the standard deviation of the sampling distribution should be theoretically um, standard deviation, which is 8, divided by the square root of n, which is 10. Okay, I could figure out what that is. I could leave it right here for now, right? Because I could plug that straight into my calculator. All right. The company finds that this sample of 8 batteries only lasted, I guess it's 10 batteries. I might have changed this hopefully in yours. So 10 batteries in 10 cars, right? 10 batteries, 10 cars. Only lasted 42.2 months. Find the probability that the sample mean lifetime would be less than 42.2 months if the lifetime distribution was unchanged. What conclusion can you draw? So I start with a drawing, right? My mean of the population should be 48. Mu equals 48. My standard deviation of the sampling distribution is here. I should put x bar. X bar is equal to 8 over square root of 10. That's going to be like 2 point something, right? And then we want to know that the sample would be, 42.2 or less. So if this is about equal to, let's call it 2.5, right? 40, boom, boom. We're probably somewhere here for 42.2. And we want to know the probability that's there or less. Does this look familiar? Hopefully it does. This is just normal CDF, right? I would put this in my calculator. It's the easiest way to do it. What's my furthest left point? That's going to be either 0 or negative big number. 42.2 is my right endpoint. The mean is 48. My standard deviation, I'm going to plug this straight in the calculator. I don't need to round or do anything like that. 8 over root 10. And that should give me right about 0.13. Okay. What does that mean? That means the probability is 0.13. This equates to, if you are more of a thinker of percentages, a 13% chance that this would happen if 48 was true. Okay. So if 48 was indeed the mean of lifetime, 48 months, was the mean of lifetime for the new batteries, a sample 42.2 months or less would happen by chance variation about 13 out of 100 times. All right. So our question is that rare? Is it rare if something happens 13 out of 100 times? It's not often, but it's not totally rare. It's not out of the realm of possibilities, right? So that's where we get into kind of a weird point, right? This is kind of a gray area. Is there evidence that it's smaller? It's kind of a little bit of evidence, but is it enough to say these batteries don't last as long? Probably not enough to justify that yet, right? Cool. So that's how it's useful. See why we're doing this whole thing is we're turning into like this could be a lawsuit, right? They're claiming that these batteries last 48 months, but we did a sample and it's way below that. You owe us money, right? Happens a lot, real world. All right, there we go. We're on to additional practice. Again, it's up to you if you want to do this additional practice or not. It's up to you if you want to do it now or save it for later. So it's up to you. If you want to do it now and you want to try it on your own, I would say pause right now. All right, I'm back. If the average weight of a Honeycrisp apple is believed to be normally distributed with a mean of 6.4 ounces and a standard deviation of zero point 0.6 ounces, find the probability that one randomly selected apple would have a weight that is greater than 6.8 ounces. So let's draw a picture, figure out what we're doing. The mean is 6.4, right? Standard deviation is 0.6. Okay. And we want to know it's greater than 6.8. So 6.8 is above this, but a little less than a standard deviation above. Okay. So, and I want to know greater than 6.8 ounces. So I want this. Okay. And notice this is just one. So this is not a sampling distribution. This is from the population. So I'm going to go normal CDF. I'm going to put in, what is it? 6.8 ounces is my lowest. That's this edge. My highest is big number. That's big enough for these apples, right? 999 ounce apple would be incredibly big. And then the mean of the population is 6.4 and the standard deviation of the population is 0.6, right? You could also think of this as a sample size of one. So you could have this, right? If it's a sampling distribution, but that's just 0.6, right? So pop that in the calculator and we get the probability of an apple that is greater than 6.8 ounces is around 0.252. Okay. So about 1 out of 4 apples will weigh 6.8 ounces or more if um, the population parameters are as stated. Okay. So if this is truly the mean and this is truly the standard deviation, about a quarter of the time we would get an apple that is that weight or more. Okay. So not very rare, right? All right. Find the probability of sample size 10 would have an average weight of over 6.8. Now we are using a sampling distribution. So this was the population distribution, right? Because we have one apple, right? Now this is a sampling distribution because we're doing a sample size and finding the average weight. Okie dokie. So things are going to change. What doesn't change is our mean is still equal to 6.4. What does change is our standard deviation. Our standard deviation of our sampling distribution, I'll write those in there, the X bars as subscripts, is equal to, it was 0.6, but now we're dividing it by the square root of 10. Our sample size, or sorry, our standard deviation of the sampling distribution shrinks as sample size increases. So that 6.8 and above is going to be from here and over. It's actually, we'll see it down here visually, but it's going to be a smaller probability of this happening, right? So I'm going to go normal CDF, 6.8, big number, and then 6.4, but now our standard deviation is 0.6 over square root of 10. Okay, plug that into your calculator, see what you get. Ooh, I haven't done it. Grab my calculator. This is exciting. All right. All right, so we're going to go to Second vars, we're going to go to normal CDF and let's do 6.8 period or enter, big number, enter, mean is 6.4, enter, standard deviation is zero point 0.6 divided by square root of 10, and we press enter and enter and enter, and we get around 0.018. Okay, so what does that mean? What does that mean? That means about 2 out of 100 samples of size n equals 10 would have an average weight of 6.8 ounces or more in repeated sampling. So if we did this a whole bunch of times, right, 2 out of 100 samples would actually end up being here or above. Is that rare? That's pretty rare, right? 2 out of 100 is fairly rare. So I would say, hey, maybe these apples, maybe, the fertilizer they're using on them or something is better, right? There might be some evidence that something's going on at this farm. They're doing a good job with their Honeycrisp apples. Good job. All right. Explain the difference between these two probabilities with the sketch of the population and sampling distribution, right? So my first one would look like this, right? My second one, right? Here's the mean, right? The second one is going to look like this, right? They're both at 6.8, which I'll make like right here, right? And we can see the difference because this one has a smaller standard deviation, right? But the same mean, we can see the probabilities would be less, right? Larger the sample size, more this gets squeezed in, right? The more this gets squeezed in. So even with the same 6.8 here, right? Because the standard deviation is smaller. Again, this is a standard deviation of zero point 0.6. This is a standard deviation of zero point 0.6 divided by root 10. So that'd be about 0.2. It's a third the size, right? It's shrinking in. Or even less than a third, right? That's not square root of 9. That's where my brain went, right? So this is a little less than 0.2. It's like 0.17 or something like that. This is squishing in, and we get less probability than this would be. So this is probability of 6.8 or more is equal to 0.25. This probability of 6.8 or more is 0.02, 25% versus 2%. Cool. There we go. Chapter 7 is officially taught, I guess you could say. We're going to practice with this. It takes a little practice, but again, putting time into this is going to help you out quite a bit. So thank you for being here, and we will see you all later. Bye.